Hey everybody, my name is Lisa Roach. I'm here from Meta, and yeah, I'm going to be talking about converting multiprocessed code to free threading. I wrote this talk as a way to sort of force myself to learn it, so I'm not a super deep expert in the space, and I think you will see me slowly lose my sanity as we get further and further into the talk. It's called Out of the Frying Pan and Into the Fire because concurrency was hard before free threading, and now it's even harder, so it's a lot of fun. For our agenda, we're going to go over our basic concurrency options. We'll talk about the challenges that you face with concurrency. We will convert some multiprocessing code to free threading, and then we will focus on optimizing our free threading code. So I only have two concurrency options I'm going to talk about today. Yes, I know async I/O is a really popular concurrency option. There's also green threads, there's subinterpreters, you can mess with the GIL with C extensions. There's lots of ways that we can do concurrency, but we're going to focus on the main sort of core traditional two, because we have limited time today. So traditionally, threading and multiprocessing have had two really clear use cases that hasn't budged much. Threading is for I/O-bound code, and multiprocessing is for CPU-bound code. If you're not familiar with these topics, I/O-bound means that we are not waiting on how fast our CPU can crunch through some work. Instead, we are waiting on some external request. Maybe we're waiting on a network call, we're waiting on a database call, file read, something like that. That's the bottleneck of our program, not the CPU. Threading is great for this. What we can do is we can launch a thread. That thread will make its external request, and then instead of sitting idle waiting for that request to return, we can launch a new thread that will make a new request, etc., etc. Then as the requests come in, we can resume our threads. This way we're able to better utilize our CPU, we speed up our code significantly, and we achieve concurrency. Now note I say concurrency, we do not achieve parallelism with threading in traditional CPython. This is because of the GIL. The GIL is the global interpreter lock. It's been the frenemy of Python developers forever. It saves yourself from a lot of pain, but it also prevents us from running threads in parallel. So we really cannot utilize multiple CPU cores with threads. So if I did want to, let's say I have any modern computing machine, and I had multiple CPUs, I wanted to run threads across different CPUs, the global interpreter lock is going to make it so that these do not run in parallel. They will run concurrently, but actually your threading code would be a lot slower doing this than it would on a single CPU. That's because there's going to be some overhead putting our threads on different CPUs and figuring all that nonsense out. If you run the exact same code on a single core, it's going to run faster because the GIL prevents parallelism from ever occurring, so you run at the same speed, but now you've just added a bunch of overhead. So we don't really use threads across multiple cores very much. Basic challenges with threading, we're going to get a lot deeper into this later in the talk. For traditional CPython with the GIL, no parallelism is obvious. We will talk more about thread contention, which is where when threads are trying to access the same memory objects. We'll talk about race conditions, which is when threads are writing to the same memory objects. And memory overhead. Generally, threads can be memory hungry, so they take more overhead from your machine. So let's go back to CPU-bound code. This is the opposite of I/O-bound code. This is when we are just waiting on how fast our CPU can run. This typically will be multiple segments of work. We are not waiting on I/O, and it's easily parallelizable. In this case, multiprocessing works fantastic. It's relatively easy to set your multiprocessing code to run across multiple different cores. I can take that workload that had 3 different areas of work, shard it across my processes, and now we're running much more efficiently. We've utilized a lot of our cores. This is the more typical way people have been doing concurrency in CPython in the last, decade or so. So why don't we do multiprocessing with I/O? Kind of sounds like the perfect solution. We're able to fully utilize our cores. There's no reason why a multiprocessed process can't make I/O calls. So what's kind of the hang up with multiprocessing that makes it so we don't choose it typically for I/O bound workloads? Well, the big difference is memory. So we said threads are memory hungry. This is because threads share the same memory space. It's really easy to share data between different threads, while for multiprocessing, it's fairly complex. If your code isn't CPU bound, a lot of times that overhead is just not worth it. So we tend to use threading for I/O with multiprocessing for more CPU bound code. So let's dig a little bit deeper into some of the problems we experience with multiprocessing, because that's what this talk is about. The first step is the setup. So setting up CPU bound code setting up multiprocessing code is more expensive than setting up threads. This is because each process is forked or spawned, which will create a new Python interpreter instance. We copy the entire state of the program. We set up inter-process communications, so maybe queues or pipes, those sorts of things. This costs time. It's slower than threads to get set up. Oh, hello? There we go. The next big thing is data serialization. So we kind of touched on it also on the last slide, but if I want to get some data from my parent process into my child process, I need to send that data to the processes. That's because they don't share a memory space. So the default serialization method in CPython is pickle. We will pickle our data, we will shard our data, we will push our data across an IPC, and then our processes have the code. This also takes time. The same works in the reverse. Every process needs to then serialize its data, send that data over an IPC. Then the parent process gets that data, it deserializes the data, and it does something with it. All of this is taking more and more time. And then, of course, the big one, which some of you probably already know, if I wanted to share data between a process, now we're starting to get really complex because processes don't naturally share a memory space. So again, I'm setting up some IPC, maybe I'm setting up queues or pipes to be able to send some pickles or whatever serialization format I'm using from one process to another. I'm serializing, deserializing, serializing, deserializing, serializing, deserializing. This takes time. So this is really the biggest challenge with multiprocessing, is that all these little things, especially data serialization and data sharing, can add up to be more expensive to use multiprocessing than an equivalent program in threading. So free threading's now starting to sound like the ideal solution, right? I can use multiple cores because I'm no longer locked by the GIL. I probably should have said that, but free threading is threads minus the GIL. So we no longer are bound by the no parallel threads rule, and I can run across different CPUs with threads in parallel. Sounds great, right? And it is pretty great if, again, we have an I/O bound process. Free threading is going to work awesome. I thought to myself, it doesn't sound all that interesting for me to show you guys some code that is multiprocess code that's I/O bound. I was like, is that really what people do in real life? Do you write multiprocess code that's I/O bound and then convert it to free threading? That would work well. So I made my life way harder and decided to write a talk on when would I write free threading code for CPU bound code. Next year, remind me that I don't need to make my life harder. And we shall see how this goes for me. So first things first, I'm going to show you guys a bunch of metrics. My machine is a big, beefy Linux server because this is a sponsored talk, so I used a server from my work. It has 80 cores and 256 gigs of RAM, so this is Mr. Beefy here. Next, I was like, let's write a super CPU-intensive benchmark. This is pretty basic. It's an expensive calculation. It's nested for loops doing math operations. There's 2,500 math operations per loop, and it's just doing, some cosine, square roots, that sort of thing. It's pretty straightforward CPU-bound code. Now it's going to get a little hairy as we go along. So I pushed my benchmarks to GitHub. I'll also include the QR code at the bottom of every slide here in case you missed it. But I know showing a lot of code on the screen doesn't read well, so I just decided to give you a little link. All right, so if we take that expensive CPU-bound code and we run it with multiprocessing, free threading, and threading, our results are kind of interesting, but not unexpected. The work to process is how many loops, so how many times am I running my expensive calculation. We can say it's 5,000 times that 2,500 math operations is how many operations I'm running. We see free threading is actually the fastest initially and then pretty quickly falls off. Threading never comes close. And then multiprocessing, as expected, does well for the medium case and well for the very large case. So this is, perfect CPU-bound code. Multiprocessing is optimized for this. So in the very beginning, small amounts of CPU work ends up being slower because we're really not doing a lot of work in our process. We're hardly CPU-bound at all. So the little bit of overhead that we are dealing with multiprocessing ends up being more expensive than creating a bunch of little lightweight threads. But it quickly tilts the other way, and we'll see in a lot of these examples there's a tipping point where the operational overhead of setting up multiprocessing becomes worth it because it works better on multiple processes than threading. So that makes sense. We talked about it earlier. It really starts to get hairy when we're sharing data between processes. So let's skip ahead and see what it looks like when we're sharing data. So I create a new variable, which is just a list of 2 million integers, and I'm going to try to share it. We will serialize this data, which means we are sending the shared data to our processes. So our first pickles, we've activated our first little pickle serialization, and we've sent it off so everybody gets it. And then we're going to access the shared data. This is every 100 iterations, we're going to look at it. And that's pretty much it. So we're doing a read-only operation. So what I expected was something to look kind of like this. We're accessing a shared memory object, but it's read-only, so we're just pulling, and we're pulling down our pickled serialized objects from this sort of shared memory that we've pushed to every process. Now what do we get? Free threading is faster in the beginning again. Free threading is now faster in the middle, but free threading still kind of sucks at the large scale. So getting a little bit interesting. Why is that? It's because of cows. Copy on write. This is an optimization that multiprocessing has. Multiprocessing does not need to use IPC or serialize read-only data. So I learned this the hard way by trying to do this benchmark, but turns out what I thought was true was not true. So I wasn't actually doing this serialization, deserialization bit. I was really just reading from that original pickle that got sent through my process in the first place. So it ended up not being all that expensive. We did end up pushing free threading to be faster for the second of the 50,000 iteration, but it's still slower for the very large iteration. So we're getting closer, like we're showing some progress, but we're still kind of a ways away. So yeah, free threading is still not overcoming these sort of negatives that threads itself has, which is it's just not optimal for processed code. All right, so we figured it out. We're going to write to shared data instead of just reading it. We're going to get around the copy on write problem. We're going to create a dictionary where we actually store our calculated results. And for good measure, we will also update an atomic counter with a little plus equals increment there. Now we've got this diagram. This should be it. We're reading and writing. We got pickles. They're flying all over the place. It's crazy. This was like 11 p.m. last night. So I was like, I really got to make sure that that free threading at some point looks good, right? So let's hamstring multiprocessing just a little bit. We gave it a really optimized workload. Let's make it like maybe more of a real-world scenario. So I unbalanced the workload just a little bit. Previously, we were sharding an equal number of work to each process. So every process had the exact same amount of work. Every CPU was working the exact same amount and ending probably at the same time. Now we're going to mess with it. Every 10th task, we're going to make just way more expensive. This is an unbalanced workload. And because I've serialized it so each CPU gets its data up front, we now have something that's going to look like this. This means one CPU will finish really quickly, and then another CPU is going to take a really long time. And my whole process is going to be spent waiting for that one CPU to take a really long time, and all these other CPUs that are faster are just sitting idle. So we've kind of messed with multiprocessing to give ourselves a bit of an edge here. Well, shit. 11 p.m. last night, it's getting late. So we tried it unbalanced, we tried it with writes. Free threading is still slower. Why is that? Well, it's really simple. Threads are hard. Threads are pretty hard. Converting code just sort of blindly one-to-one between multiprocessing and threading was not working for me. It was not able to beat the performance of multiprocessed code, which has had however many odd years optimizing itself on CPUs. Free threading is brand new. It's still under construction. There's still a lot of corner cases to be worked out, and I was really struggling to sort of optimize it and make it work for what I thought, in theory, should work. So let's talk a little bit about why. We've gone through some of the challenges earlier on, but we'll revisit them in more detail. So we have thread contention, race conditions, and then free-threaded adds the fun unknown factor, the little spice of life. So thread contention and thread starvation. Thread contention is when threads compete for shared resources. Sometimes threads never get access to the shared resource, and that causes thread starvation. We're probably not seeing thread starvation because our process does complete in a relatively reasonable amount of time, but it's very likely that we are seeing thread contention. This also can affect cache, which I actually think is probably what's happening here. Cache contention is thread contention specific to cache. Multiple threads will compete for the same cache. One thread will not be able to get access to the cache because another thread is there. So what might happen is threads get booted to higher level memory, which is slower to access and can slow us down, especially as this happens at scale. Yes. Then there's cache invalidation. Cache invalidation happens when both threads are trying to access cache at about the same time. One writes to the cache, it invalidates the cache that the other thread was going to pull, and now it again has to boot up to higher memory, take a little bit longer. Now we showed two examples, one where it was read-only and one where we read and write. So should we be experiencing cache invalidation with the read-only one? Sure are. Python was always writing. Python's writing reference counts. And we actually have seen this play out in real life, so other people smarter than me figured this out a little while ago, where this is a merge sort benchmark. The red line is CPython with free threading. I think it's 313T. The blue line we'll talk about later, but we see our merge sort benchmark around the 50 thread mark almost exactly just shoots up. It starts taking way longer. This turned out to be reference count contention. So many threads were trying to write reference counts that everything just couldn't do it, got locked up, slowed down, our performance went through the roof. So this kind of looks a little bit like what we might be experiencing with our code. Sometimes when you think about cache, you're thinking I'm accessing the same memory location over and over again. But is it true that our threads are accessing the exact same memory? Probably not. But what can also happen is that when cache is located in memory addresses close enough to each other, that you can get share cache line misses. So even if you're not accessing the exact same memory, if your memory is close enough together on the chip, you still basically get cache misses. So super fun to debug. Oh yeah, this is called false sharing. So it's not literally the exact same code, but doesn't matter. You still get cache invalidation anyway. The next thing, of course, is race conditions. This might not be the cause of our slowdown, but let's take a look at what our counter says. Our counter we expected to be at 50,000 or 500,000 or 5,000, whichever one you're looking at, but the actual counter value is almost 1% less than what we expected it to be. This is because we were experiencing a race condition. A race condition is when two threads are trying to write to the exact same memory address at the same time, or one thread is writing to a memory address at the exact same time another thread is reading from that memory address. Whatever it is, we end up with a slightly wrong number. This is pretty interesting. So we had this line of code, task completed plus equals 1. I think this is interesting because this is a problem also in GILful Python. The GIL we tend to think of as, this perfect locking mechanism, everything is super thread safe, but the reality is we can have race conditions in the GIL as well, and we probably just don't really talk about them because people don't run threaded code at scale. But if we did, we would have noticed this probably. So x plus equals 1, if we look at the bytecode, it's not a single operation, it's multiple steps. This is x store fast, we're storing x as 0, and then we increment 1. So what can happen between those two lines is a thread can come grab this and interrupt, or a syscall or something like that can come stop this process from happening, and it happens rarely, but enough that if you do it at scale, it adds up to be, almost 1% of my counter is wrong. So let's talk a little bit about how we would optimize threads, and it's 4 a.m. now. We got to get this done. So first, we know pretty obviously that there's a race condition. Let's just start there. Let's add some locks, see what it does for us. All right, we added some locks. Free threading is a little bit faster, but it's not blowing me away. It's still slower than multiprocessing. So let's keep going. There's a library on GitHub that one of my coworkers has written. It's called ftutils. I've included the URL and how you would install it with UV. This is a pretty nifty library that contains a lot of utility code that can help make free-threaded code more performant. The first thing we'll talk about is local wrapper. Local wrapper was designed specifically for this reference count problem. What it does is it prevents objects from being incremented or decremented except at creation and destruction of the local wrapper. So we basically prevent reference count contention. So if we go back to this original chart, the blue line is merge sort, but we've wrapped all of the numbers with the local wrapper. So now we no longer have reference count contention, and you can really see how it has greatly improved performance. I'm also going to throw in some data structures because it's late and I'm desperate. So we're going to throw in a bunch of highly performant, free threading specific data structures. Actually, they work for GILful threads as well. We have concurrent queue, concurrent dict, and atomic in64. Concurrent queue and concurrent dict both they're what they sound like. They're queues and dicts, except they are optimized to be able to handle push and pops from multiple threads or concurrent reads and writes from a dictionary. It uses a whole bunch of those local wrappers under the hood. It has some optimizations so that way we reduce the amount of contention while still maintaining performance. And then atomic in64, this creates a 64-bit integer that can be updated atomically. All integer operations become atomic, so x plus equals 1 must complete, it cannot be interrupted, and therefore we can stop ourselves from race conditions without specifically adding lock all over the place, which is pretty nice. So now, finally, we've done it. Free-threaded is faster than multiprocessing. It's significantly faster. It wasn't the easiest thing I've done. I did hamstring multiprocessing on purpose, so I guess I could have tried this all without that in there, but I didn't. I was tired. So yeah, we've made it. It was interesting. Our race condition is solved. It's actually cool. You can use the atomic N64 around the Gilful Python, and you will also see the same race condition be solved, which is kind of fun. But race conditions are hard. You know, I made a very basic benchmark that was really obviously a race condition, but in real life, this would be silent, you know? Would you have noticed 0.9% being slightly off? You have to really be paying attention. They are non-deterministic, be a different thing off every time, maybe, maybe not. Unpredictable. So really what we need is a thread sanitizer for Python, which is something someone on my team is working on. It's not available yet. I was hoping we could have it done by this talk, but we don't. So keep an eye out for thread sanitizers for Python. It can help you identify data races. And then the last thing, of course, is the unknown. Free-threaded Python is super, super new. It's still barely out of experimental phase. It's really not something people have used yet. So you can make Stack Overflow questions that won't be marked as duplicate. Your LLM does not know how to write it for you, so great job security. But you're on your own a little bit. Figuring out this talk was definitely harder because there wasn't, you know, a wealth of blogs to refer to and books and prior knowledge from years and years like we're used to. So when would I use free-threaded instead of multiprocessing? If your process is severely I/O bound, probably makes a lot of sense. If your startup costs, for whatever reason, are very high, maybe you're making a lot of processes, maybe you're pushing a lot of data to those processes. If you're doing a lot of message passing between processes, or just generally lots of shared data between processes, that's probably the big one that I would watch out for, is if you're sharing a ton of data between processes. Threads share memory space, so can become more efficient. And then, of course, use at your own risk. Free threading can be great for high-performance computing. It's really made for high-performance computing, but it's hard to use, and it's not yet ready for production. If you have questions, join the free threading Discord. There are lots of very smart people who can answer your questions and be helpful to you. And I also include some helpful links on the last page, but I think this maybe is more interesting to people. So that's it.
Let's take one or two questions.
Amazing talk. Great visuals. This made my day. Thank you so much. I do have a question regarding I/O bound versus CPU bound. I often deal with a lot of data that usually exists in pandas data frames or just in general data frames. And the one thing that is not always clear to me is when processing data that has to be in partitions, and I'm just literally doing a for loop over it, sometimes it's not clear to me if I could convert that to just like I/O bound by putting it in a table, or is it still more CPU bound, so I should go to multiprocessing?
Pandas data frames are going to be kind of special because I'm pretty sure they're written in C. So it's already super optimized. Like, it's already going to be faster than if I were to use a Python dictionary or something like that. I think you would be better off doing it in a for loop than putting it somewhere else and pulling from there. Just because I think it would be so optimized already under the hood that I assume it would be faster than the network or the I/O call to open a file, read a file, or like pull from a database.
Okay, thank you.
Hi there, great talk. I have two questions for you. One's a fun one. How did you generate those images? They were really, really fun. And the more serious one is, I guess I'm used to thinking that locks slow your code down, like not even looking at the multiprocessing side of the house, right? Just looking at what you did. You had multi-threaded code without locks running slower than multi-threaded code with locks. And I can't wrap my head around that, so could you explain how that happened?
Yeah, so first, this was all in Google Slides for me. I don't know, this was like a generate image button on the side, and I could prompt it. So I guess there's an LLM somewhere drawing these images. They were pretty fun to make. So then your second question was, Oh, it was just in my head, but you can't give me two questions at once or else I forget. Say it again real.
Got multi-threaded code to run
Yeah,
faster
with
with locks.
Yeah. So to be fair, it didn't really run much faster when I added a lock at all. I don't know if I have it up here, but yeah, so this didn't really help it very much, the actual locking. Let's see how much it did help. Honestly negligible. Like the way, how non-deterministic all this is, like the 1 second difference probably isn't a real difference at all. So I don't know if I'd say the locks, like that lock made it faster, but when I started adding stuff like concurrent dict and concurrent queue and things like that, those do have locks under the hood, but they're actually written in C, and they're super low level, and they're very, very fast. So it's giving me a more optimized way to do the reads and writes and to scale without hitting contention. So even though locks, like, yes, they're slower, if you're using them to prevent thread contention, you actually do speed up your code if you do it right. If you do it like the dumb way I did it, then it won't. But if you're doing it in the smart way where you're putting it around code that really needs locks in a really quick manner and like you are doing it at a low level, then your code will be faster because you don't experience contention.
All right, thank you so much.